chat. You can raise your hand, you can wave in the window. And so Linda will be watching, and she'll unmute you if you have a question, or if you type it in the chat, she can ask it. So feel free to jump in at any time to get clarification.
And the only thing I'll add is we're recording the session. If anybody has an issue with that, you can turn off your camera or go radio silent. We'd love other people to be able to see this great talk. And if you're watching the recording, welcome. You're going to have a good time.
All right. With that, Dr. Basri, I'm going to hand it over to you.
Thank you, Renee. Let's see if I can get my screen shared here. Does everyone see that?
Yes.
And do you see my cursor?
Mm-hmm. Yes.
All right. Then let the show begin. And, as Renee said, this is really not intended to be a lecture where you just sit there and listen the whole time. We have a small group of folks so that you can ask questions and we can discuss. I'm perfectly able to modulate the talk depending on how much discussion we get into. So yeah, feel free. So the topic for tonight is are red dwarf planets habitable? And I'll tell you about red dwarfs in more detail in a minute. But the reason this topic is kind of very current is that essentially all the announcements over the past, I'd say 8 years of Earth-sized planets in the habitable zone of other stars have actually referred to planets around red dwarf stars. And there are a bunch of reasons for this, and I'll get into them in a minute. But it appears that red dwarf planets in habitable zones might be the main sort of prime real estate in the galaxy, at least insofar as planets in habitable zones go. And so red dwarfs are not like our sun. So it's really a very big question. Are they actually habitable? And that's what we're going to talk about tonight.
So the first question, Dr. Basri. So our sun is not a red dwarf, it's a yellow dwarf, right? So it's a hotter star than the red dwarf. Will our sun ever become a red dwarf? After a few billion years, it'll expand into a red giant, and then what? Will it ever become a red dwarf?
Yeah, the terminology in astronomy is kind of funny. So there's lots of dwarfs in astronomy, a lot of giants. And actually our sun will end up as a white dwarf. So I guess there's a lot of colors too. They're not the same kinds of things. So these terms are used a little loosely, I would say. The sun is called a yellow dwarf, but it's not really a dwarf in terms of, if you look at all the stars on the main sequence, and the main sequence is where stars spend most of their time. So the sun, you may have heard the sun is an average star. It's not. The sun is actually a larger than average star. It's about twice as massive as the average star and twice as big. And that's because the average star is a red dwarf. But even red dwarfs are actually a somewhat heterogeneous class. So the red dwarf class starts at sort of half the mass of the sun, but it extends down to essentially the brown dwarf limit, so less than 1/10 the mass of the sun. So red dwarfs are themselves a rather diverse class of stars. But the important thing about red dwarfs is they're the most common star. So that's why the average star is a red dwarf. About 3/4 of stars are red dwarfs. And because of that, most of the stars in our solar neighborhood, or any neighborhood in the galaxy, are in fact red dwarfs. This picture at the bottom here is a sort of 30 light year 3D representation of what's around our sun, which is in the middle of the picture. And you can see most of those stars in there are red dots, and those are the red dwarfs. To look at it another way, here's a plot of all the stars near us, and again you can see most of them are red dwarfs. Stars like the sun are yellow in this picture, so you can see it's not an average star really. The blue ones are more massive than our sun. The orange ones are a little less massive, but most of them are these red dwarfs. Another interesting thing about the red dwarfs is the first red dwarf that will ever die will do so about 10 times the current age of the universe from now. So every red dwarf that's ever been made is not only still around, but it's still kind of in its infancy. They live, the time scale they live depends on their mass. So the half solar mass ones live about 100 billion years, which is like 10 times longer than the sun does. And the low mass red dwarfs live like 1 trillion years. So in the very distant future, the universe, as it sputters out and makes no more stars, will be entirely red dwarfs at that point. Another thing that we've learned in the last decade since the Kepler mission is that smaller stars tend to host smaller planets. And in that sense, the Earth is a smaller planet. And so Earth-sized planets are more common around red dwarfs as well. And so put all those things together, and that's why nearly all the nearby Earth-sized habitable planets are around red dwarfs. Okay, so I'll say a little bit more about the red dwarfs. Well, they're red. The redness comes from the fact that they're cooler than the sun. So the way incandescent light happens is based on temperature. The hotter things get, the bluer they get, the cooler they are, the redder they get. So as I said earlier, the red dwarfs are sort of a half to a tenth the size of the sun, also the mass of the sun. Their temperatures are sort of less than half the temperature of our sun. So our sun's around 6,000 Kelvin, and the red dwarfs are around 3,000 Kelvin, down to 2,500. But the real big difference between our sun and red dwarfs is their luminosity, how bright they are. So they're somewhere between 1% as bright as our sun and 1/100 of a percent as bright, a factor of 10,000 times fainter for the 10th solar mass red dwarfs. And that makes a huge difference. If you're talking about habitable planets and your star is so much fainter, you need to go a lot closer to the star to stay warm, basically. And so that's the big difference between planets around red dwarfs and planets around our sun. If you want them to be nice, have a nice temperature, they must be much closer to the star than if you have a solar type star. Okay, there's other reasons though that all the news stories are about habitable planets around red dwarfs, and that is that Earth-sized planets are actually kind of hard to find in the habitable zone of a sun-like star. The Kepler mission that I was involved with was trying to find Earth-sized planets around sun-like stars, and that was right at the limit of the capability of that spacecraft. And we didn't really find any, Earth 2s, true solar analogs, a real Earth-sized planet around a real sun-sized stars at the same distance as the Earth is from the sun. And we kind of knew that was going to be a stretch. And it doesn't really matter, because if you find planets closer than the Earth is to the sun, but the star is a little fainter, that's kind of the same situation. And the red dwarfs are the easiest targets because the habitable zone, as I said, for red dwarfs is quite close to the star. And that sort of helps all of our planet finding techniques. So you may know that originally exoplanets were found by this kind of wobble or radial velocity technique. And there you don't see the planet at all. You just see the effect of the planet on the star that it's orbiting. It pulls the star around a little bit as it orbits, and we can detect the motion of the star due to the planet. But the closer the planet is to the star, the more it'll pull on the star. And of course, if the star is smaller, it'll also pull on it harder. And so those things all work in favor of finding Earth-sized planets around red dwarfs. The other main technique for finding planets around stars is the transit method. I'll go through these in a bit more detail in a minute. But basically, the technique requires the planet to block light from the star. But it's easier to block more light, a bigger percentage of light if the star is smaller. So for the same size planet, there's a bigger dip in light because of a same size planet for a smaller star. So that also makes red dwarfs easier. And then, you know, planets that are closer to a star orbit the star faster. Their years are shorter. So if you're watching, the planet will go around, you know, many times, and that makes it easier to find compared with, say, the planet only goes around once a year, like the Earth does. So for all those reasons, well, actually, there's a final one. Also, closer stars are easy to look at, right? They're closer. And so since most of the close stars are red dwarfs, again, you know, so everything basically is in favor of finding Earth-sized planets around red dwarfs. And we have a bunch of them at this point.
So I think that's the really cool point, is that not only are red dwarfs super plentiful, but they're easy to find planets around. So that helps us, in a sense, do this search for habitable planets, right?
Well, especially habitable Earth-sized planets.
Yeah.
It turns out to be pretty easy to find Jupiter-sized planets around bigger stars, because the planets are bigger too, and they pull harder on the star as well. But Earth-sized planets were very tough. In fact, the radial velocity method really hadn't found any Earth-sized planet or Earth mass planets. The Kepler mission is the one that found them. And that's for these reasons that I've given you.
Okay.
Okay, well,
I've got a quick question or a comment or whatever. When you look up in the sky and you see all of the stars above your head, if you go to a really dark sky, isn't it true, or I've been told that most of those stars are not red dwarfs, you can't see them. So what you're looking at are bigger, beefier stars, even on a real clear night, and all these red dwarfs are there. They're just very difficult for your eye to see it.
Well, in fact, they're impossible for your eye to see. So the very closest star to us is a red dwarf, Proxima Centauri, and it cannot be seen by the naked eye. And then all the rest of them are further away, so they're even fainter. So yeah, when you look up in the sky, you don't see a single red dwarf, even though the sun is surrounded by them. They're just too faint for the human eye, unaided human eye. So you need.
Which is really cool, because that means that there's all these Earth-sized planets that are orbiting potentially around all of these stars we can't see.
Yeah, no, that's right. I mean, the sky is probably full of them, but you don't, you're not aware of them.
Can you see them with amateur telescopes, or do you need?
Oh, you can see them. You can see them with amateur telescopes. Yeah.
Okay.
Some, right? But they're very faint. So as I said earlier, you know, they're somewhere between 1% and, you know, and one in factor of 10,000 times fainter than the sun. So if you put them, oh, actually, let me go back to this slide here. This actually showed the distance to the star of these planets that are found. So here's Proxima Centauri. It turns out to have an Earth mass planet, maybe. I'll get back to that later. We don't actually know the size of that planet. But, you know, that's 4 light years away. And that's the very closest star. But, you know, here, this one's 13, 14, 22 light years. That's considered the close solar neighborhood. So that, yeah, they're pretty close, but can't.
We have a question in the chat from the Rashids. I assume that's from the household. Would you be able to see our own sun from across the galaxy as a star?
No. So our sun, we could see our sun. So we can see sun-like stars out to something like 1,000 light years from here. The galaxy is 100,000 light years across. So you definitely could not see it.
And another really good question from Asan. What's so special about the size of the Earth?
That's you know, anthropomorphic. What's so special about it is we live on an Earth-sized planet. That's essentially all that's special about it. But, you know, humans are very interested in Earth-sized planets just for that. And now I've realized I misspoke about how far you could see the sun, because the absolute magnitude of the sun is 5th, and your eye can see down to about 5th, which means you could only see the sun out to about 30 light years from here with your naked eye. So yeah, even the sun's not that bright. So the stars you actually see when you look up are much brighter than the sun. They're much more luminous, I should say, than the sun, and they're further away. So most of those are higher mass stars that you're actually looking at. Okay, so planetary transits is the method that gets us the Earth-sized planets. And that's, just the planet crosses in front of the star. But of course, what are the odds that's going to happen? Well, it turns out the odds are basically given by this. It's the diameter of the star divided by the diameter of the planet's orbit. So this is where the red dwarfs help, because the diameter of the star is smaller. And the diameter of the orbit means that the smaller orbits are going to give you a higher probability of seeing a transit. And so but the habitable zone for red dwarfs is smaller. So those both help, basically. I'm going to skip that slide because we are a little slow. So here is what we saw with the Kepler mission. This is the size of the planet on this axis. So here you can see that this is the Earth, this is Neptune, this is Jupiter. And this is the orbital period. It's logarithmic. So this is the star, the planet goes around the star every 1 day, every 10 days, every 100 days. So the Earth is right here somewhere, basically. As you can see, Kepler found a lot of planets that were close to the star. They have short orbital periods and smaller than Neptune and down into the Earth-sized and below. And this is a very incomplete sample here because, again, those get harder to find. So it's probably true that, the bunch down here, or for that matter out here, is many more than you see on this plot. So we have to interpret a plot like this, knowing how inadequate our methodologies are. So basically, after computing all those sort of missed planets that we think are there, we conclude that there are tens of billions of Earth-sized planets in our galaxy, based on this kind of statistics here. Okay, well the transit gives you the size of the planet, just tells you how much light the planet blocks. If you want to know the mass of the planet, then that's where the wobble method comes in. So basically the idea there is, as I said, the planet is pulling on the star. So the star is moving around a little bit. It basically orbits the center of mass between the star and the planet. So in the case of our solar system, here's actually the path of the sun. And of course, there's more than one planet in our solar system, so they're all pulling on it. So it executes this rather strange little orbit. That orbit is, way inside the sun. So the sun is sort of just kind of moving around like this, around a point that's near its center, but not at its center. And the velocity at which the sun moves on this weird path is, it's kind of the velocity that your car goes. It's like 10 meters per second. And we have to detect a Doppler shift due to that motion. And the way Doppler shift works is the precision you need is basically the ratio of the motion of the star to the speed of light. So that's like trying to ask, I want enough precision that I could tell the motion of my car as a ratio of the speed of light. Well, as you know, light goes around the Earth 7 times in 1 second, and your car definitely doesn't do that. So it's a very tiny ratio. And so it was only in the 1990s that we got good enough, precise enough to measure that motion. But the motion tells you sort of how massive the planet is, if you know how massive the star is. And we know how to figure that out from other issues. The only problem with this method is if the system, it only tells you the motion towards and away from you. So if the system was flat on, you were looking down the pole, there wouldn't be any motion towards and away from you. So you wouldn't see this wobble. And if you're in the orbital plane, that's the best example. The planet will come right at you and right away from you. And so if you don't know anything about the tilt of the orbit, this method only gives you a lower limit on the mass of the planet. So the sweet spot is, I got a planet, it transits, so I know I'm in the orbital plane, and I can measure the wobble. Then I know everything about both the size and the mass of the planet. And that means I can get the density, at least the bulk density of the planet. And so it turns out that there's something funny going on. If I go back to this plot, the question was, what about all these planets? Here's the Earth, and Venus, of course, is the same size as that. Here's Neptune, and Uranus is the same size as that. And in our solar system, there's nothing in between. But obviously in the galaxy, there's plenty in between. And so what are these planets here? Are these kind of like large Earths, or are they like small Neptunes? That became a real question. And the answer comes from detecting what the density of the planets are. So does it have the density of Neptune, or does it have the density of the Earth? And what we found is that, and I won't go through the details here, but here's planet density and here's planet size. And this is kind of the line you would expect if it was a rocky planet. And up to about 1.5 times the size of the Earth, the planets we found are kind of along this line here. So we do think those are larger Earths, super Earths, if you like. But then the line turns down. And so the planet gets bigger, but the density is dropping. So those are lower density planets. So they're clearly not giant rocks. They're more like mini-Neptunes. And the break point is about 1.5 times the size of the Earth, which is something like 4 times the mass of the Earth. So if anybody who claims they found a super Earth in the habitable zone, but the radius of that thing is larger than 1.5 Earths, that's not a habitable planet. Why is it not? Well, the reason this density drops like this is we think these planets have a big rocky core to them, but they also have an envelope of hydrogen and helium on the outside. And the envelope is opaque enough that when you ask, how big is the planet that blocks the star, the atmosphere is able to block the star. So the size we get is caused partly by this atmosphere. So you can add a little bit of mass to the planet, but if it's all hydrogen atmosphere, the planet can get significantly bigger. And so if you ask them, okay, well, let's say it's only 1% hydrogen. So it's a big rocky planet with 1% hydrogen. And it gives me the size I see. What's the condition like at the surface of the planet, the rocky surface? And 1% hydrogen turns out to be an atmosphere where the bottom of the atmosphere will have a huge pressure and a huge temperature in order to support the atmosphere, basically. So it definitely won't be habitable. So we think these are mini-Neptunes here and not habitable, even in principle. And it's only in here that they would actually be habitable.
So we have a few questions. The first one was, why are they called dwarfs? So referring to the red dwarfs and the yellow dwarfs and brown dwarfs.
Yeah. They're called dwarfs because they're small compared to the giants. Literally.
Seems like we need a more PC name.
Yeah, maybe. So the dwarfs, those stars that we call dwarfs, and as I said, the sun is, you can call the sun a yellow dwarf, but it's actually pretty big. They're burning hydrogen in their core. They're on the main sequence of stars. This is what a star does for most of its life. They have relatively stable luminosities, and we only call them dwarfs because when the hydrogen runs out in the core of the star, it swells up to a much larger size. So our sun will, be 30 times bigger and 1,000 times more luminous when it runs out of hydrogen in its core and starts burning helium. Causes the star to swell up and get much brighter. So those are called red giants. And so the dwarfs are just dwarfs in comparison to the giants. It's kind of silly, I have to say. Then the brown dwarfs and the white dwarfs are kind of not burning anything, and they're much smaller. So those dwarfs are way smaller than the yellow dwarfs and red dwarfs. So it's a bad kind of terminology.
And then the next question was, how did the data of the sun's wobble get collected?
Well, I don't think it actually did get collected. We can compute that very easily because we know our solar system really well. You can measure it, but of course you're measuring it from the Earth. So that's the Earth's going around the sun, so you have to fix all that anyway. But we know what the sun's motion would look like from another star. That's really what we're talking about there.
Got it. And then one question I had on this slide is actually, well, what about life forms that can survive an immense amount of pressure and heat? Like we've discovered like snailfish at the bottom of the Marianas Trench where we didn't think anything would be able to withstand that pressure, right, at the bottom of the ocean. And we've found life that exists near hydrothermal vents, like very hot climates. So, like, what do you think? Is this way beyond even that? The kind of pressure that would it be in these Neptune-like?
Yes, actually, it is way beyond. So that there, the pressures would be, you know, thousands of atmospheres. Well, at the bottom of the ocean, the pressure is very, very high.
Yeah.
But at the bottom of the ocean, the temperature, you know, is it's still liquid water. Whereas at the bottom of the hydrogen atmosphere, the temperature would be a couple of thousand degrees. so even metals would be melting. So we don't think Earth-type life could exist there.
Right.
Well, this is what I want to say with this slide. The concept of habitable zone isn't really, could there be any sort of life there? You know, and then the Star Trek fans could, you know, ask about the Horta. But what we really mean by habitable zone is if you took the Earth and you put it where this planet is, would all life die or not? That's really kind of what it means. Because as you're quite right, there's life at the bottom of hydrothermal vents. And we think that, you know, like Jupiter's moon Europa has hydrothermal vents, you know, has a salty ocean and reasonable pressure and temperature and volcanic activity at the bottom of the ocean. There's no reason why you couldn't have similar life on Europa, but Europa is totally not in the habitable zone. In this use of the term. So, okay. Yeah, so you have to be careful about what it actually means.
Okay.
So as a yes,
Gibor,
go ahead.
We had another question about the planets that you were pointing at on the previous picture. If they have like an atmosphere, we were learning Earth only has auroras because of the magnetic field from the core, and Anavi was asking, because Mars doesn't have a magnetic core and all the atmosphere blew away. Does that mean that all of these have hot magnetic cores for them to have atmospheres?
The atmosphere doesn't have anything to do with the magnetic core in the way you've asked it, but we're going to come back to that issue later. So, yeah.
Okay.
Hold that thought.
Okay, perfect.
Okay, so as I was saying, the concept of habitable zone does not tell you in any way whether life is there or not. It just tells you if you put the Earth there, would life continue or not, really. And it's mostly about if you had an ocean, would the ocean, you know, boil away? Would it freeze solid, or would it be an ocean? That's kind of what it really has to do with. But you know, it's clear that if a star is putting out less energy, you need to go closer to it to get those same conditions. So that's really the main point here. So the sun has, you know, some kind of habitable zone around it, and a red dwarf has a much smaller habitable zone around it just because it's so faint.
Gibor, does that mean that the solar, oh, sorry, I guess the same version of our question, different version. Does that mean the solar wind is like 1% as much as our sun's? Because that's what we had learned, that like, that's why Mars doesn't have air, is the solar wind blew it all the way.
Well, I'm going to get to that.
Yeah, okay, same. Okay, cool. Thanks.
Yeah, that is a big issue. That's a big issue, and I will get to it. So I won't dwell on why we think water is needed, except that all life on Earth needs some kind of water. But I'll just mention that habitable zones are a little more complicated than just how far are you from the star and how bright is the star. First of all, you know, of course, you need an atmosphere. So you can put an Earth-sized planet in the habitable zone, but if it doesn't have an atmosphere, clearly it's not habitable, at least not in the usual way. And as you all know from the climate change debate, the greenhouse effect can seriously affect the surface temperature on the planet. And so far, we really don't know anything about these Earth-sized planets in habitable zones. We don't know anything about their atmospheres, really. So let's just consider that to be, you know, an unknown. And when people claim they saw a habitable planet around a red dwarf, you can just dismiss it. It's like, yeah, okay, well, it's in the right place, but what's its atmosphere like? Does it have any water on it, for example? We don't know about any of those planets really yet. I won't dwell on this one either. Well, so Venus is an Earth-sized planet. We say it's not in the habitable zone because Venus isn't habitable, But if it didn't have such a huge greenhouse effect on Venus, it would be much more pleasant than it actually is. So that shows you right away that there's an issue here. And if you took the Earth and you moved it a little bit further away, it would freeze over. In fact, it has frozen over even sitting where it's sitting, and then got out of that. So that it's just more complicated than it might seem. And the Earth the sun has actually increased its luminosity by 30% since we know there were oceans on the Earth. That's a much larger change than we're talking about with climate change now. And yet somehow the Earth has maintained liquid oceans through all of that. We know that from fossils. And so the Earth has a complicated scheme for maintaining its habitability, having to do with how much carbon is in the atmosphere and how much is in the rocks. And I'm going to pass on that one right now, but you can ask about it later too. And then finally, as I just said, the sun is actually changing its luminosity as it burns. As the hydrogen turns to helium in the core gets denser and the sun gets a little hotter. And so the habitable zone also moves with time. And in fact, the Earth is not going to be in the habitable zone in another 500 million years or so. The sun will have gotten bright enough to boil our oceans. So we actually only have another 500 million years on the Earth as a habitable planet. So that's some real climate change when that happens.
Start shopping for some new real estate.
Well, yeah, we probably going to want to move planets by then.
Yeah.
Okay. Now, what about red dwarfs? Well, actually, let me say one more thing here. Red dwarfs don't have this problem because, as I said earlier, they live way longer. So for the whole age of the universe so far, once you make a red dwarf reach its stable luminosity, it's there. And, you know, another whole age of the universe, it's still there. And, you know, and you can go several ages of the current ages of the universe before the red dwarf does anything untoward. So they're much more stable that way. Okay, but there are some downsides to red dwarfs, and this is a big one. In order that the planet have a decent temperature on it, it has to be reasonably close to the star. And unfortunately, it's close enough that it gets tidally locked to the star. So the star is close enough to the planet, it just distorts the planet into a bit of an egg shape. And then the egg wants to orient itself so it's pointing at the star. That's exactly what happened to our moon. That's why we only see the front side of the moon, because the moon has been tidally locked to the Earth. And that would happen to these planets. So you can see if you're on the planet, it's not that the planet doesn't spin, it does spin, but its day is, well, it's not really its day, its spin period is the same as its year. Now, if you're standing on the planet here, you can see the star overhead. Here, you can still see the star overhead, and here and here. In fact, if the star's overhead, it stays overhead. So there's no rising and setting of the sun on these tidally locked planets. And, you know, perhaps more importantly, the backside of the planet never sees the star. So it never receives any starlight, so it gets cold. And this was the main beef against red dwarf planets up until 15 or 20 years ago. People thought it's going to be so cold on this backside here that the atmosphere will actually freeze out back there. And, you know, you get liquid nitrogen and all carbon dioxide, you know, dry ice, and the whole atmosphere just freezes out onto the backside of the planet. That was obviously a bad scene, not habitable. Luckily, we have models. I guess I'm going to go here. We have models now. If you just put the Earth's atmosphere on one of these planets, basically the front side gets heated, but then that creates a higher pressure, and then the air tries to flow around to the back, and you set up this huge jet stream and carry heat from the front side to the back side. And it's enough heat to stop the atmosphere from freezing out. So we know even if you put the Earth there and locked it like that, the atmosphere would not freeze out. Now, obviously, we have a continent on the Earth, Antarctica, where the sun doesn't shine half the year, and it's, you know, it's kind of nasty. It's frozen and cold and so on. The dark side of these planets would be worse than that, because you never shine the sun on it, but it would not freeze the atmosphere out. So they would be icy, very icy on the backside, but not uninhabitable in that sense. And of course, if you had an ocean, planet-wide ocean, for example, it would have an ice crust on it, but underneath that, the ocean would also carry heat around to the backside. So this is not a a showstopper in terms of habitability. I mean, it's not Earth-like, but it's not a showstopper either.
But the winds and the currents would be very, very strong on that planet, right?
Yeah, they would be. They would be strong. How strong would they be at the surface versus in the jet streams and so on? So people can run climate models. We have all these climate models on Earth. You can just take the climate model and put it do the red dwarf and do the tidal locking, and so people have done those models. So they know, yeah, the wind is kind of shrieking at the jet stream altitudes. And yeah, it's windy. It's windy at the surface, but not not uninhabitable. Yeah, but not really like the Earth either, of course. Okay. Then the other thing about red dwarfs is they don't look like the sun. Remember, they're half the temperature, so the quality of light is also different in this sense. So those high mass stars, the ones you see with your eye, are more massive than the sun. And they're hotter, and so they have more ultraviolet light. So the bulk of the energy shifts towards the ultraviolet. And of course, the ultraviolet's not great for life. We have our ozone layer to protect us, but if you go to these two solar mass stars, it's mostly ultraviolet, and that would be bad. But we don't care about them anyway, because those stars are short-lived compared to the sun. So there's not really time for life to do much anyway. So who cares? Sun-like stars, well, you know what they're like. The low mass stars emit primarily in the infrared. So infrared is kind of heat radiation. It's what you see in night vision goggles. It's not true that they don't have any light in the visible, but the bulk of their light is coming out in the infrared. Okay. So actually, here's what the light looks like. This is a wavelength of light here. This might be too technical for some of you. Doesn't really matter. The point is your eye works between these two vertical black lines here. This stuff over here is ultraviolet. It's really bad for you. And over here, this is the infrared radiation. And you can see for a red dwarf, the bulk of the star's luminosity comes out there. Why do we care? Well, and also you can see, I mean, this is part of the reason they're faint, right? So they actually, if your eyes worked in the infrared, you probably could see red dwarfs with your naked eye. But because your eye works here and the stars are faint, you just lose.
Sorry. Oh, go ahead. Go ahead.
No, go ahead.
So I checked up on this too. Apparently some vampire bats and mosquitoes have eyes that work in the infrared range. So they'd be perfectly fine because, of course, mosquitoes can survive anywhere.
Yeah, sure. They'd be fine. Yeah, I mean, we'd be fine too, right? Because there is visible light there. It's just this much. So you would see the star would look actually kind of orangey to you. And it would be faint. It would be faint compared to the amount of energy it's giving to the planet. But when you try to compute what's the surface temperature on the planet, you want to worry about this stuff. And then the point I wanted to make here is, what the planet actually absorbs depends on what the planet's atmosphere is like and what the planet's surface is like. So if it's all clouds, it might reflect a lot of the light away. So that means you can move the planet closer to the star and it still won't be too hot. Or, at the same place, if it's cloudy, it's going to be cooler than if it wasn't cloudy. And whether it's rock or ocean will make a difference. But I put this here. This is snow, this line here. This is how reflective it is. So obviously you all know in the visible, snow is really reflective. So the sunlight, our ice caps reflect most of the sun right back off. In the infrared, snow is actually dark. So if you had a snowy planet around a red dwarf, it's actually absorbing more energy than it would be if it wasn't snowy. So So that's another example of things you have to worry about. Okay, now we're going to get to the magnetic fields that Sunil was asking about. All stars produce magnetic fields because you just need, you need a conducting fluid, and stars are plasmas, so they're conducting. You need some kind of boiling motion. The high mass stars have boiling motion in their cores, and stars like the sun and the low mass stars have boiling motions near their surface, so you got it somewhere. And it needs to rotate, and all stars rotate, basically. So you're going to get some kind of magnetic field. This is what our sun's magnetic field does. So it starts off looking kind of like a magnet, but then the equator of our sun goes around faster than the pole, so it winds the field up. And then finally the field gets too stressed, and you get all kinds of explosions and interesting activity. And then the field relaxes again and it starts over. So that's the solar cycle. And if you look at the sun in the visible, it's pretty boring. You don't see that field basically, except for sunspots. These little dark spots are places where magnetic field is coming up. But if you look in the ultraviolet, the sun starts looking much more interesting because the magnetic field heats the upper atmosphere, which emits in the ultraviolet. And so you can see that better in the UV. And this is the sun in X-rays. So this is super hot stuff. It's the solar corona. It's 1,000,000 degrees. Remember, the surface of the sun is 6,000. There's this 1,000,000-degree plasma around the sun. That's entirely due to the magnetic field. And the magnetic field is sort of shorting out and dissipating, and that's what heats this outer atmosphere. But that, of course, bathes the planets then in ultraviolet and X-ray radiation. And so that's important. So this is pictures of the magnetic loops coming out of the sun. This is an X-ray picture. This is a UV picture. So as I said, you can see the fields much better if you go to the high energy radiation, and they're producing the high energy radiation. But that's important for planets around the star. You also get these disruptions of the field, and the sun, you know, spews out a huge amount of hydrogen at very high velocities. And so if you have a planet out here, it can get hit by these coronal mass ejections, and those travel through the planetary system as well. So now if you remember what I said about red dwarfs, they're a lot fainter than the sun in their main energy, so we move the planet very close to them. But it turns out red dwarfs are just as active and even more active magnetically than the sun is. So I've taken the planet, I've put it right up against all this stuff here. And that's an issue for sure. You know, so the Earth has its own magnetic field that acts as a shield for us. So the sun fires stuff at us all the time. There's the solar wind, which we're constantly hit by. And then there are these blasts of plasma from these explosions. And usually that gets diverted around us by our own magnetic field. Some stuff gets through and comes down around our poles, and you get the auroral ring. And it's these particles from the sun that get in and come down in our magnetic field and hit our atmosphere that creates the aurora. You know, but it's not dangerous. But it would be far more dangerous if we didn't have the magnetic field, or if the sun were much more active, or if you took the Earth and, you know, moved it right next to the sun. That would all get much worse. And unfortunately, that's what you do with red dwarf planets. And so these explosions on the red dwarfs are actually much, much stronger than the ones on our sun even. They can be 1,000 times more energetic, and the X-rays can be 1,000 times brighter when the red dwarfs are young. So the planets are really subjected to a pretty toxic environment early on. The red dwarfs settle down magnetically after a few billion years. So if you could wait that long, you'll be okay. But those first few billion years are pretty hairy. And these flares on the sun, we can't see them in visible light. But on red dwarfs, A, the star is fainter, and B, the flares are bigger. So sometimes the star will get brighter by a factor of 50 for a few hours. Imagine if our sun did that. The whole sun got brighter by 50 times. That would be a problem also. So red dwarf planets in the habitable zones have all this to deal with, basically. So some people don't think they are going to be habitable. but I'll give you reasons why they might be able to get around that. So the main point about this is what Sunil was asking about earlier. You've got this blast of high energy radiation and particles from the star. You move the planet right next to it. And if the planet doesn't have a magnetic field, this is going to strip the planet's atmosphere over time. And in fact, that is what's happening to Mars right now. So we actually have a spacecraft in Mars measuring its atmospheric loss as the solar wind just picks up protons in the Mars atmosphere and carries them off. And that's why Mars has that's one of the reasons Mars has such a thin atmosphere. Mars is also smaller than the Earth, so it can't hold on to it as well. But it would have a much better atmosphere if it had kept its magnetic field.
Gibor, we have a question about Mercury from the Rashids.
Right.
They want to know that since Mercury is so close to the sun, does it get hit by our solar flares? And if it does, what happens?
Yes, it absolutely does get hit. It gets hit harder. It has more X-ray flux on it and so on. Mercury has no atmosphere. So, it doesn't have to worry about losing its atmosphere. It already lost it if it ever had one. So Mercury is like the moon. It's just a dead rock, basically. So yes, it does get pummeled by the sun, but I guess it doesn't care very much anymore. Venus, on the other hand, has a thick atmosphere. So Venus is closer to the sun than us, and Venus has no magnetic field either. So you'd think maybe Venus would have lost its atmosphere, but it hasn't. In fact, it has atmospheric pressures 90 times the Earth's atmospheric pressure at the surface of Venus. So clearly an Earth-sized planet can survive more flux than we get here. Now, why is it such a thick atmosphere? That's because all the carbon dioxide on Venus is still in its atmosphere. Essentially, all the carbon dioxide on the Earth is in rocks, in limestone, and in our interior. And why did that happen? Our oceans basically dissolved it and made rocks out of it, and it's stored there. And this climate change debate now is us pulling a little bit of carbon dioxide out of the ground and putting it back in the atmosphere. But that's a minuscule amount compared to the total amount of carbon dioxide that was on the Earth early and that got converted to rock. So Venus still has its atmosphere because it left all that in the atmosphere. However, the sun did strip what it could strip, and it stripped the hydrogen off of Venus. And so Venus doesn't have any water anymore because remember, water is H2O. It's hydrogen and oxygen. So it turns out it's hard to strip these heavier atoms off. So carbon, oxygen, nitrogen, things like that can survive this blast from the star. But hydrogen and helium are too light, and they will be stripped out. And so Venus was nearer to the sun enough that if it had oceans, and we think it did, they were boiling. Or it didn't really have oceans, it had steam. And the steam was then subjected to this intense activity from the sun, which broke the water into hydrogen and oxygen, and then the hydrogen was stripped away. And so that's why Venus is it's got two big problems. One is this 90 bar CO2 atmosphere, which is an enormous greenhouse effect, which makes the surface really hot. And the other thing is it lost all the hydrogen, so it has no water. So Venus is not a habitable planet, or at least we don't think so. Maybe, there was this story that maybe things are living in the atmosphere of Venus. I don't know, but the surface is definitely not habitable.
So one question. Oh, go ahead.
No, I'll take the question, yeah.
Did somebody else have a question? No, okay, I'll go. So how did Venus have water before then? If it was closer to the sun anyway, it had this thick atmosphere anyway, so it was so much hotter anyway. How did it even start out with liquid water?
Yeah, so, the question is, how do you assemble the planets when you're making them? And basically the solar system will be pretty dry in the inner part of it because it's too hot for water to condense, basically. But as you go further away from the sun, you'll start having water and other molecules condensing. Basically, it's a huge cloud or not a huge disk of comets, out beyond the snow line, which is sort of out beyond Mars. And then if if those comets' orbits get perturbed by Jupiter or whatever, some of them end up in the inner solar system. And if they hit the planet, then you get the water onto the planet. So something like that. Even the Earth may have gotten its water that way as well. But you basically build the water in as you're building the planet. And then the question is, you know, how much, and we actually don't know how much water is inside the Earth. We know how much is on the surface, obviously, but the water content of the mantle is still a bit of a mystery to us. And that's going to be important a little bit later as well.
Okay.
All right, but yeah, so basically water is a common molecule during the process of star formation. And the issue is, you know, do you deliver it to these inner planets or not? Also, we've now learned that planets can also change their orbits quite a bit. You could form the planet out past the snow line where there's a ton of water available, and then move it in closer later on. So we see examples of that as well.
Okay. Another question that just came up is, do we know when Venus lost its water then?
Yeah, it lost it pretty early on, you know, in the first billion years. Okay, so those are the two big questions about red dwarf planet habitability. Can you keep water on the planet? And can the atmosphere survive this blast from the star? And in the case of red dwarfs, there's one other problem, which is this, that remember, they're very stable when they settle down onto their main sequence, luminosity, but they're very slow. Remember, they live slow and die slow. They also are born slow. So the red dwarf comes down off of a very bright state more slowly than our sun does. This is millions of years here. So our sun is actually much brighter than it is now when it's forming. It's just, you form it out of the gas cloud, and it then contracts down to its regular size. While it's contracting, you're dissipating gravitational potential energy. Turns out that's a much more efficient way to make the star shine than nuclear fusion. So our sun was, you know, 40 or 50 times brighter right at the beginning, but it settled down pretty quickly, like within the first 10, 20 million years, to its almost current luminosity. Whereas the red dwarfs take their time about it. So 100 million years later, it's still 2 or 3 times brighter than it's going to be, and so on. So you ask, you know, where's the habitable zone around the red dwarf? You ask it about the red dwarf's stable luminosity. But when you were making the planets, the red dwarf was significantly brighter than that. So if it was going to have nice oceans in the main phase, they'll definitely be boiling during this early phase. And that's when the star is also magnetically most active. So this is, you know, this puts the planet at great risk for losing its water and its atmosphere because the star is a lot brighter for too long, basically. And it's very magnetically active then. And the habitable zone later on is too close. So those are all issues that may, you know, some people say, oh, look, this is too much against red dwarf planets. They probably aren't habitable. That would be a terrible shame since most Earth-sized planets are around red dwarfs. So now I'm going to try to save them. So yeah, how are we going to preserve water, for example? Well, you could just, you know, store it inside the planet. As I said, we don't know how much is in the Earth's mantle. So if you have a planet, especially if it's a little bit bigger than the Earth, it has more volcanism, and you bring the water out after the star has settled down, so after a few billion years, basically, then the water is safe. So maybe you just, you know, you just have to wait longer for red dwarf planets to be habitable, but they'll get that way. And remember, you got all the time you want. The red dwarf's going to be there for 100 billion years. So even if it took longer than the current age of the universe to make the planet habitable, it might be. But of course, that's not interesting to us since we want to know, is it habitable now?
So isn't the core of the planet hotter? So would the water just be in steam form or something? Or
it actually, it's very high pressure inside a planet as well. So it's locked into molecular bonds with rock, basically.
Okay.
And when it gets blown out in lava, then it gets free.
Okay.
Yeah. And then we talked about comets before. So, you know, maybe you just need to resupply the water after the star has settled down. And so you could, you know, and in our solar system, Jupiter cleared out the comets pretty early on. But in red dwarf systems, Jupiter-sized planets are much rarer. So you may end up with a big disk of comets, which is not strewn out into space by a giant planet. And they could slowly impact the inner planets for quite a while. Now, of course, you know, that's what killed the dinosaurs. So maybe, again, maybe you have to wait a few billion years while you resupply the water and endure all these giant impacts. And then eventually it clears out and then the planet becomes habitable. But at least that would be a way to put water back on the planet afterwards. Or I also mentioned, you know, maybe you just migrate the planet. You keep it out away from the star till the star starts to behave itself, and then you bring the planet in later. That's, you know, we see systems where that has clearly happened. It would mean that the percentage of, you know, inhabitable red dwarf planets is smaller than the number that we see by some amount, but you could have it. Or, you know, here's a fun one. I said we didn't freeze the atmosphere out on the dark side of these tidally locked planets, but you sure freeze the water out. So yeah, I mean, maybe you just tidally lock the planet, all the water ends up on the backside in ice, and then, you know, you have volcanoes and things later that melt a little of it and put the water back into the atmosphere. This one is actually, you know, almost certain to happen, essentially. So there is a nice cold trap on the backside of every red dwarf planet where a lot of water is almost certainly frozen, and it's just a matter of how much of it gets unfrozen later.
So with the comet impacts, is that really likely if you have a red dwarf that's not that gravitationally attractive, and then you have this tiny planet that's also not very big? Do you still have a large percentage of these comet impacts? Or is that going to be
sure, it just depends on, you know, the red dwarf is smaller, yes. It has less gravity, yes. All that means is the orbital velocities at any given distance are slower than they would be if the star was bigger.
Okay.
Otherwise, it's kind of the same, right? So, so you can have orbits at any distance from the star, and if you don't scatter all those comets away by some giant planet, a lot of them are gonna remain in a disk around the star afterwards, and then you have to perturb them slowly, and some of them get into the inner system. Okay. You know, someone might argue, well, that's not good because the planet will be incessantly, you know, subject to giant impacts, and yeah, that potentially. But as we'll see in a minute, these planetary systems actually have lots of planets, or they can, and so, you know, a given planet may not get it that much. It may have several guardians further out that catch most of the comets. Finally, you know, there's another way to do this. Those Mini-Neptunes we were talking about before, remember they have excess amount of hydrogen, right? Too much. Well, okay, but let's put that right close to the red dwarf and let the red dwarf savage it and get rid of almost all the hydrogen, but not quite all. You know, that would be another good way to sort of preserve the right amount of hydrogen. If you start with way more than you need and let the star strip most of it away. And we actually see directly a few exoplanets where we see hydrogen being stripped off by the star. We can actually see the cloud of hydrogen. You know, if you use hydrogen light, essentially, to observe the system, you get a much bigger transit than if you use visible light, where just the planet blocks it. Now you get the whole tail of hydrogen loss blocking starlight in that particular wavelength. So we see that directly. So we know this happens. The statistics of the Mini-Neptunes also show that there's a population of them that clearly have been stripped near their stars. So this for sure also happens. So if you just, again, though, it's, you know, it means fewer planets would end up good because you need just the right combination of excess hydrogen and the right amount of stripping by the star. Okay, then, you know, now I'm going to be a little more speculative, you know. So you have these planets, you know, frozen side. Maybe this side's all dry and hot. Maybe the twilight zone is the right place to be on these planets, right? Because there's a big temperature gradient here. So somewhere it's a very nice temperature. So that's real estate. That real estate's very valuable. Or, you know, you can say, all right, I have a planet and it's locked and it's kind of too far away. So that preserved the ocean, you know, and the ocean's mostly frozen, but right at the substellar point where the stars overhead, it's warm enough to melt the ice there. So you could get a planet like this, and that would be easier to preserve water on. You know, is this habitable or not? Why not?
So we had another question in the chat. If the tidal locking leads to a freeze out of the atmosphere, would this not set up a runaway effect where the whole atmosphere freezes out in the dark?
Yeah, so that was what people worried about before, but our sophisticated climate models now show that even the Earth's amount of atmosphere carries enough heat around to the backside that it keeps it warm enough that the atmosphere does not freeze out. So the atmosphere circulates backside, front side fast enough to never freeze out. So we're confident that that's the case for one Earth, you know, 1 bar atmosphere. Yeah, if you have a 4 bar atmosphere, even better. So no, it's not really a problem. And then of course the question of the dark side, it's probably something like extreme Antarctica. Maybe nothing lives on the surface, but maybe stuff lives under the ice, especially if there's, you know, liquid water under the ice, like with Europa, which is incredibly cold. If the planet is geologically active enough, it'll keep the deep ocean liquid. You know, that's one good thing about water is when you freeze it, it floats. Most things, when you freeze them, they sink. The frozen form is denser, but with water, it's the opposite. So you can have an ice shell and liquid underneath it. And you know, all our worries about what the star's doing don't really matter on the backside here. You never see it. No radiation of any sort hits this stuff. So it may not care whether there's an atmosphere on the planet even. But I mean, there should be. Let's see. Okay, so let me just go through a couple of known systems. As I said, this is the very closest star to us, Proxima Centauri. It's a companion to a solar type star and a slightly less than solar type star, Alpha Centauri A and B, which is this pair here. And then Proxima is closer to us than that pair, but it travels with them. So it's captured by them. And here is the Proxima system. So it has a planet that's in a very close orbit. It's in the habitable zone of Proxima Centauri. And we found it by the wobble method. So we know that it's at least 1.3 Earth masses. We don't know the tilt of the orbit, so it could be more, but the statistics say it's not a lot more, probably. And we don't know the size, so we don't really know if it's a Mini-Neptune or not. So that's cool, but it's, you know, kind of dubious. Here's a better one. This is called LHS 1140b. That planet's right in the middle of the habitable zone of that star. And we do know its size and mass, and they're all kind of Earth-like. They're within that super Earth realm. So here's the transit dip due to that planet, and here's the wobble due to that planet. So that's pretty good. That one looks all right. It's a little massive, so it's 1.4 Earth radii and about 6.6 Earth masses. So I don't know, it's definitely a super Earth anyway. So the surface gravity on that planet would be 3 times that on the Earth. So you would weigh 3 times as much if you went there. So you probably don't want to go there. Then there's this system, which is really amazing. It's called TRAPPIST-1 because the astronomers who found it like Trappist beer mostly. And this actually kind of looks like a mini Jupiter system. So here's our sun. Here is TRAPPIST-1 to scale the red dwarf. And here's Jupiter. So you see it's not a lot bigger than Jupiter. Here are Jupiter's 4 Galilean moons. And this has 7 planets that are at least the size of the Earth within a similar distance. Okay, but that is the habitable zone for this star because this is a very, very low mass star. So seven planets are packed inside what would be Mercury's orbit. and they all have masses and sizes comparable to the Earth. We have actually detected water on more than one of them. So that's kind of an amazing system. And it does show that you could have water in the habitable zone around a red dwarf. So we'd love to be able to study these planets more. There are a bunch of multiple systems known. So apparently nature doesn't have a lot of trouble making Earth-sized planets, and doesn't have a lot of trouble putting them in habitable zones either. So that's good. Okay, so that was the main gist of the talk, and of course I'll take questions of any sort now. Thank you.
So that's exciting. Yay. I love the last few slides, because like now I'm excited to find life on other planets. So I want to know, like, what's the next step? So what else is being studied about the TRAPPIST system and other systems to determine if they're truly habitable? Are we looking for atmospheres? What are we looking for next?
Yeah, that's kind of the next step, is to try to understand the atmospheres on these planets. So the James Webb telescope, which has been delayed and delayed and delayed and delayed, is actually supposed to launch this year. Fingers crossed. It's been supposed to launch many years in the past, but it keeps getting closer. So people are relatively optimistic. If that's a 6-meter telescope that operates in the infrared, and would be able to measure the atmospheres. I didn't include a slide about that, but basically the idea is when you have a planet, let's see, let me go back to all the way up here. I guess I'll use this one. So let's say this is a red dwarf and an Earth-sized planet, because it would scale something like this. This is what Jupiter would look like against our sun, but you reduce the size of the star and you reduce the size of the planet. This is kind of what the Earth would look like against a red dwarf too. Okay, so you can see as the planet transits, so you have to have a transiting exoplanet. As it transits the star, some of the starlight is going to come through the atmosphere of the planet. The planet's blocking starlight, but there's the atmosphere too. And in fact, I already said, for these mini-Neptunes, the atmosphere can make the planet look bigger, right? If you have that enough hydrogen, it looks bigger. Well, that's the same idea here. So if you just have a regular atmosphere, the planet will be slightly bigger. And if you use a spectral line that's formed in the atmosphere, the size of the planet will be slightly bigger than for a spectral line that is not formed in the atmosphere and where the rocky surface creates the transit. So that's essentially the technique. And James Webb will be able to do that with molecules like water, so that they have spectral features and we know where they are, and it has a spectrograph and it has enough aperture and sensitivity. And we have a mission right now called TESS, which is surveying all the nearby stars for transiting planets. So we expect to have, we already have a number of good targets for Webb to try to actually measure the atmospheric composition of some of these planets. It's hard for Earth-sized planets, so they'll be doing it for, super Earths and mini-Neptunes first, but that's where this is going. And then there are techniques that are still under development that would allow us to actually image the planet separately from the star. That's much harder actually, but it can be done and will be done 10 or 20 years from now. And then you can take a spectrum of the planet directly and tell what its atmospheric composition is. So that's the next step, basically.
Gibor, you've got a question about intelligent life, life we can communicate with. I've got, this is from the Rashids, but I have one to add as well. Is it reasonable to assume that intelligent life may have come and gone in some other world across the universe? And my added question is, what do you personally think? Because I know some astronomers think that there may be reasons why we're alone, and others think there's billions of communicable civilizations. Right. What do you think?
I think that the first question was put right. And it turns out how long intelligent civilizations last is the main factor about whether we're going to hear from any or not. On my website, actually, there's a page called, SETI, or is anybody out there, or something like that, where I go through the numbers. And what happens is you can be very optimistic about everything. So, when we started, in fact, when I wrote that page, we hadn't found exoplanets yet, but I said, let's be optimistic, because we already understood that star formation probably leads to a lot of planets. So let's figure every star has planets, which turns out to be basically true. And, and let's figure most planetary systems have a habitable planet, or one in a habitable zone. That's also not far from wrong. And then you start getting into more speculative stuff. But, the Earth had life on it soon after it was possible for life to be on it. So let's say life tends to form quite commonly, if you have the right conditions. So you can go down the line like that. And you get to the last thing, you're trying to figure out, will we hear from somebody now? So the question is, are there other civilizations around at the moment? If you think you can't really hear them from across the galaxy, how many are close to us, and so on. And it turns out that if intelligent life, that is to say life that would broadcast radio that we could recognize as artificial, if that only lasts for a few thousand years, typically on a planet, we're not going to hear anything, because A, the galaxy is really big, and B, it's been around for 10 billion years. So you could have had tons of civilizations come and go, but the number that's around right now would still be like one, and that would be us. So that is the big question, and the bottom line there is, if civilizations don't last for astronomical lengths of time, we're probably not going to hear much. So that's maybe, and by astronomical lengths of time, I mean like millions of years. If you go under millions of years, turns out it's very hard to make the numbers work out. And if you want the nearest civilization to be within 1,000 light years, it's definitely way hard to make it work out. So that's how that goes. On the other hand, what's not included in the Drake equation is the question, are some civilizations immortal? Because if some are, then of course those just accumulate over time. And so, we have no idea. so that's kind of where we're at the moment with that. There was another part of it, or did I answer it all?
No, I think you did. And there's, I've got another question from Pamela Harmon. What was the most surprising star or star characteristic that was found via the Kepler mission data? What was the most surprising thing?
About the stars?
So Pamela, do you mean about the stars, or do you mean about
the planets?
The planets? Let's see if I can unmute her.
She said yes about the stars.
About the stars.
About the stars, okay.
Well, I think, and this is an aspect of the Kepler mission that has gotten much less press. There's a new branch of astrophysics called astroseismology. So our sun, it turns out, because it's boiling, basically, it's vibrate. It's like a bell that's being rung by the boiling motion, and it kind of vibrates in all kinds of modes. And we can measure that on the sun, but that's pretty hard to measure on other stars because we have no spatial resolution on any other star. But it turns out their brightness jitters due to this ringing, and Kepler was sensitive enough to pick that up. And so we knew that, we kind of knew that ahead of time. So there was a group of astroseismologists as part of the project. And they spent a lot of time developing very sophisticated ways to try to pull the frequencies of vibration out of these stars. And then it was very fun. The first meeting we had after the mission was operating. We had reports from various teams, and the astroseismology people came in and they said, well, the bad news is we wasted all our time on this software to develop the periods, because the good news is you can just do a Fourier spectrum of the light and plot it and use a ruler to measure what the periods are. It's like they stick out like a sore thumb. And those periods act a little bit like seismology does for the Earth. So you can actually probe the interior structure of stars with those. And I'd say the most amazing thing is they were looking at red giants. And with a red giant, remember the star has kind of burned through the hydrogen in its core. It now has a helium core, and that's burning much more brightly. The atmosphere of the star has swelled up tremendously. They could measure the rotation of the helium core inside that. And the right metaphor is if you had a hot air balloon and there was a marble at the center of the hot air balloon, and the marble was spinning and it causing the outer part of the balloon to move slightly, you could tell how fast the marble was spinning. And they were able to pull that off. So that was, I found quite amazing. They could also tell what kind of red giant it was by the way it was vibrating exactly, something that had been confusing before. Lots of other fun stuff about stellar oscillations and so on. So yeah, it was quite a bunch of surprising results came out.
Wow. Anyone else have any questions? I think it's just fascinating the amount of things we can learn from our instruments nowadays about stars and planets that are millions of light years away. We can tell atmospheres. I find that just incredible.
Yeah, I think, that's the fun thing about astronomy. We can't get our hands on any of this stuff. So it's all detective work, and, you come up with new techniques and new instruments, and computers help a lot. And even just taking the spectrum of a star, you can tell, that's what I do. I study spectra at high resolution. I can tell you, what the star is made of, how turbulent the surface of the star is, how fast the star is spinning, what the magnetic field is on the star, all kinds of stuff that, it's just, you have to know the physics and make the measurements and then put it all together.
That's incredible. Anyone else want to get your questions in? I think it's been awesome.
There's somebody who's got his hand up there.
Raj.
Let's see. So why are we going to Mars instead of going to these red dwarfs where we know there is likelihood of water on the planet?
Well, that's a good question with a really easy answer. The red dwarfs are way, way, way further away than Mars is.
Okay.
But there is this breakthrough, what's called breakthrough starship or something, that Yuri Milner, who actually lives in Los Altos Hills, who's a Russian billionaire, is funding a study of a potential mission to Proxima Centauri. And the way they want to pull that off is that you build an array of super bright lasers that can give you a charge of 1 gigawatt. You get a pulse of laser light that's got a gigawatt of power in it. Then you orbit above this laser, or comes by at the right point. You have a little chip, the backside of which has to be 99.99999% reflective, otherwise the laser is just going to vaporize it. But if you can pull that off too, and then you put a bunch of electronics on the front side of the chip, and the whole thing weighs 3 grams or something, and it gets hit with this gigawatt of laser light, it accelerates to 20% the speed of light in about 5 minutes. And you aim it at Proxima Centauri basically, and hope it gets there. But the fun thing about that project is you've got the laser array. You can fire it off once a day. These chips are easy to make, so you can just keep shooting. And if you miss most of the time, that doesn't really matter. And so it takes the chip about 20 years to get to Proxima.
Wow. Wow.
The trouble with that mission is that it goes by Proxima at 20% the speed of light.
Oh, you can't slow down?
You can't slow down. So So it turns out the amount of data you can collect is not really better than if you
In fact, it would be
really
worse.
Telescope on the moon and try it that way.
Wouldn't it be worse? Better. Yeah, I mean, I can't imagine you get anything.
Well, so then people, having realized that, got smarter. They said, well, maybe we could slow it down. Okay. And the way you could slow it down would be you'd have to pack a very tiny little reflective sail on the front of it that could be deployed. So maybe you could get a few meters of surface area, turn it around, and then use Alpha Centauri, which is much brighter than Proxima, to slow it down like a
as a brake.
The trouble is Proxima is 40,000 AU from Alpha, so you don't want to slow it down too much, otherwise it'll never get back to Proxima. So anyway, somebody worked out, what's the optimal mission here, and so you can pull the whole thing off in like 100 years, and then it comes by Proxima much more slowly.
And then of course you have to sort of ask yourself, well, what is the technology on Earth like in that time period?
That's correct.
So why are you bothering? Because by the time it gets there, it's obsolete.
They hadn't really solved the problem of how do you message the data back down to
exactly
either from this tiny little chip. So my feeling about that one is you're probably better off building a big telescope on the moon that can resolve the Proxima system directly and just do it that way. You probably learn a lot more that way. It's probably, I don't know, it might be comparable expense.
We're seeing the whole Chin family now, I just noticed. Hello. The entire family just came on. They've been anonymous since now.
That's awesome. So another similar question, like, are we aiming SETI messages? So SETI is the search for intelligent extraterrestrial intelligence. Have we aimed SETI at some of these systems to check if we're getting any radio signals from there?
We have a SETI expert online, actually. Pamela Harmon works at SETI.
Good.
Have we done that? Do you know?
Hi, everyone. Well, we've only, the Institute, and I can't speak for, everybody around the world, but the Institute has only sent, a message a couple of times. We're actively collecting data, but we're not actively sending a message.
Yeah, so they've looked at most of these red dwarf planets, at least some, to see if somebody was transmitting. There's a big debate among the SETI community and the broader community about whether it's a good idea to send messages to these places. Because, do you want to alert the aliens that, we have a technological civilization under development here? I personally think we're already broadcasting our presence pretty clearly. So I'm not sure that's a worry, but yeah.
Yeah, I mean, there's certainly the difference between sending a message and then what leaks from our atmosphere, which, our leakage declines, the more we leave radio and go into, cable and fiber optics. And there's certainly more than one view, but at one extreme, we should not be sending a message, to broadcast our position in the galaxy and the universe, and because of negative side effects, what could happen. And then there's the other end, which is let's see what's out there, let's see who responds.
Yeah, it's an unresolvable debate, because you could say, well, the only civilization that's out there is the one that wipes all the other ones out, and so we don't want to reveal it.
Yeah, there's so much science fiction, so many science fiction stories that lead us to believe that is the only outcome.
I just want to add to that I work with Tibetan Buddhists in India, and when I was teaching them about the search for extraterrestrial life, and they said, if aliens ever come to Earth, and I'm expecting the doom and gloom thing, they said, are we prepared to help them? Because they're probably coming because they need something. And my jaw dropped because I'd never considered that possibility. That, are we prepared to be compassionate, and what are we planning on doing for them? I'm like, oh.
If they got here, they're probably well beyond our development. So I'm not really coming for help.
No, but it was an interesting perspective. It's like, what are we prepared to do to help them? It's like,
well, Pamela made an interesting point a minute ago, which is, remember I said a civilization has to exist broadcasting radio for some amount of time. If we're all on fiber optics 100 years from now, that means the Earth only broadcast radio for 200 years. If that's typical, then yeah, we're totally not gonna hear anything. But it doesn't mean there's not a ton of them out there. So yeah, you can go all kinds of ways with this stuff. By the way, I'm gonna teach an Osher Lifelong Learning Institute course starting in April called Science Fiction or Fictional Science, and we're gonna talk about some of these things in there. I'm hoping to have this kind of conversation in that course.
Fantastic. Any more questions from the audience? I think it's been a fantastic discussion, and I hope you all have learned something. I know I've learned a ton, and I'm continually fascinated and inspired by looking to the stars.
And thank you all for listening and supporting the ASP.
Yes, thank you all for supporting the ASP.
Yes.
Great job, guys. Amazing job, everyone.
Thank you
guys
very
made
much.
Saturday night so powerful.
Thank you, Dr. Basri. I'm a fan. I love hearing you speak whenever I get the chance.
Thank you. Thank you. Good night, everyone.
All right. Thank you, Dr. Basri.
Good night, everybody.
Thank you, Linda.
Thank you for coming.
Goodbye.
Bye-bye.